So if it's just me and the box, I say I applied a force to the box. The work done on this box was done by me, and it's whatever the weight is times the distance I've moved it, right? But if you think of it from the work energy theorem, what is actually happening is I am doing work on the earth to take this box away from it. And the earth is doing negative work on this box to give it potential energy. So the net work done on this box is 0 because I did the same amount of work on the earth that the earth does on the box. And instead, the energy transfer was that this box now has potential energy. That's two ways of looking at the same problem, and you get the same answer, but I find it very boring. I realize it's important. It's important to define your problem when you're doing physics, of course, but when we're doing elementary problems like that, the discussion on like, well, technically the Earth is also moving in the galaxies, and it's just like, it's not important. If I take this box and I rip it away from the Earth, and then the Earth does negative work on the box to give it potential energy, my body, me, I am the person doing the action. I am the thing applying the force, but the Earth is what gave this energy. Right, that's kind of interesting. I did the force, I did the forcing, I did the push, but the Earth gives this potential energy. I don't give it potential energy. So when you're looking at these problems, it's not always obvious what is doing the action and what is giving the energy. Work is a transfer of energy. When we move things, we're taking energy from someplace and putting it another place. And the physics accounting becomes important to track where all of that's going. That's cool. Okay. But it doesn't really answer the question, does it? Does it? I have a box. I have a magnet. Did I do it? Okay. I'm going to try to actually... Okay, I have a box and I have a magnet. The magnet picked up the box. I didn't pick up the box. Hopefully. I can't really tell. I'm scared of magnets. Hopefully you saw the magnet pick up the box. I didn't pick up the box. If magnetic fields cannot do work, what did the work? What picked up the box? I've seen magnets pick up cars. What's doing the work? And you think that below the little boxed text, there would be an explanation for that. Let me read it to you. Magnetic forces do no work. This follows because V cross B is perpendicular to V, so V cross B dot V is 0. This is what I was saying before. The velocity and the magnetic field vector directions are always perpendicular, so when you dot them back into the velocity, you will always get 0. Magnetic forces can do no work because the Lorentz force equation holds. Right, that's what he's saying. Magnetic forces may alter the direction in which a particle moves, but they cannot speed it up or slow it down. The fact that magnetic forces do no work is an elementary and direct consequence of the Lorentz force law. But there are many situations in which it appears so manifestly false that one's confidence is bound to waver. God, I love Griffiths. He writes such fun sentences. Okay, when magnetic crane lifts the carcass of a junked car, for instance, something is obviously doing work, and it seems perverse to deny that magnetic force is responsible. Well, perverse or not, deny it we must, and it can be a very subtle matter to figure out what agency does deserve credit in such circumstances. This is the little nugget of interesting thing I was talking before. I pick up the box, but I do not give the box potential energy. The Earth does that. The magnet picks up the box, but the magnetic force is not doing work on the box. So something else must be doing work on the box. And then he says, I'll show you several examples as we go along. And then his problems. And then he talks about currents. So just a note, I feel like that's bad. I specifically remember sitting in like a week of lectures where I was ignoring what the professor was saying and I was trying to figure this out. Maybe I'm an idiot. Maybe you got it from what was happening in that small paragraph, but you say something is doing the work. What's doing the work then? because something is doing the work. It would be great if you did show me, and I'm sure he does. I was, of course, an undergrad, and undergrads are just notoriously bad at reading books. You gotta read the books, actually. So I'm sure if I were to just keep this in my brain and focus and read the rest of this book, he would have explained to me what was happening. But he did not. And as I said earlier, I just put this in my brain as like, okay, magnetic forces do no work. I know the equation, I get it, but what's doing the work? And I went to grad school and I took Jackson E&M and it just never came up again. Like, we did work problems. So why was I so confused in this book? And I think it's because he doesn't explain what's doing the work. Like, that would just be a great moment to say, and here's an example. But he says, well, we'll do it. It's coming up. Second thing I want to say is nobody send this to David Griffiths, because I think he hates people that talk to him about this. He is so snarky in this new chapter. He must have received thousands of emails where students were like, but I've seen cars picked up by cranes. Like, I can pick up a paperclip. What are you talking about? And he's so mad about it that this chapter is specifically for those idiots like me who are like, okay, but I'm a little confused by what you wrote down. Like, I get it. I agree with the Lorentz force law. I understand. But what's doing the work, though? Here's my evidence for that. So this is section 8.3, magnetic forces do no work. And there's a note that says, this section can be skipped without loss of continuity. I include it for those readers who are disturbed by the notion that magnetic forces do no work. And I'm not disturbed, man. I'm just confused. Like, I'm not disagreeing with you. You just need to explain it to me better. I understand the Lorentz force law, but I see this happen in real life. So just tell me what's actually happening. I'm not disagreeing with you yet. Spoilers. So he does an example of a big electromagnet picking up a junkyard car. And he says, you flip on the electromagnet. Well, this is my interpretation of what he says. You get it. Okay. So you flip on the electromagnet, there's a changing magnetic field. The little magnet particles in the car get an induced current around it, a Faraday EMF, right? Or an induced EMF. And in addition to that current that is now on the car, there's a changing magnetic field due to that. So in the magnet, there's another little induced EMF called emotional EMF. And the interaction of those two currents is what lift the car up. They increase the potential energy of the car. Watching a magnet pick up a car, you are watching the electric force do the work, but the magnet is providing the energy. Just like me picking up the box, I'm applying the force, but the earth is doing the potential energy. Okay, fine. This whole section, he's just very salty. The fact that magnetic fields do no work follows directly from the Lorentz force law. So if you think you've discovered an exception, you're gonna have to explain why the law is incorrect. And I just, like, it's not that I think the Lorentz force law is incorrect. It's that I didn't understand what was picking up the car. I didn't understand what was doing the work if it wasn't the magnetic field, or the force due to the magnetic field. So, I mean, you could have just put that in. I've already recorded this video and I learned some new information. So first, let me tell you what I said in the first version. He's got a little section in here where he says, if you found an exception to the Lorentz force law, if you've found a reason for magnetic forces to do work, you have to change the Lorentz force law to account for that. And he says, for example, if magnetic monopoles exist, the force on a particle with electric charge QE and magnetic charge QM becomes this. I think I've talked about this in a different video. So in that case, a magnetic field would do work on magnetic monopoles. But, magnetic monopoles don't exist. So this isn't a valid case. But he's using that as an example of like, okay, but the Lorentz force law would change. But then he says, a less radical possibility is that in addition to electric charges, there exist permanent point magnetic dipoles, parentheses, electrons, question mark? Why? What's happening? This is what confused me in the last recording of this video. I thought this was a joke because electrons do have permanent point magnet dipoles. They have quantum spin. That's what an electron is. It has a spin vector, and magnetic fields can do work on spin. They can do work on point magnetic dipoles, and they do. But anyway, the end of this video, magnetic forces can do work, unless you're thinking completely in classical electrodynamics, and then you have to come up with a bunch of currents to solve the problem. And that's okay, but I mean, we could just do quantum mechanics instead. But I mean, we could just do quantum mechanics instead.
But I mean, we could just do quantum mechanics instead.
Okay, bye. I still insist. In classical electrodynamics, magnetic forces cannot do work. Simple as that. Open and shut case. Follows straight from the Lorentz force law. You said relativistic mass isn't a thing, but it's in my textbook. Here. See? It's on Wikipedia. Are you telling me that Brian Greene, celebrity string theorist, knows less about relativity than you, a YouTuber? But I'm a medical doctor, and I took the one required physics course to get into medical school. And so I learned all of relativity because I am a medical doctor. And I learned that when you're going really fast, you get more massive, and that's why you can't go the speed of light. I learned that in school. Guys, I think this woman is an idiot, because here's a video of literally Albert Einstein saying E equals mc squared.
Furthermore, the equation E is equal mc squared.
Why do we even watch this?